Hello, my friends. Pretty quick one here. Some of this slide in particular, we've already talked about. We just haven't formalized it in a slide, so good idea to do that. And then the next one is another application of this idea with a new part of it too. So I guess what we're kind of in right now are, along with the motor, the DC motor, these are good applications of well, magnetic forces that are exerted on moving charges. So, in this case, what we're trying to represent is what happens if we move a charge through a magnetic field. Well, we already know that, all right? And if you use your right-hand rule, thumb to the right, fingers into the page, your palm will push down in the direction of the force exerted on this particle. And so the particle moves something like that. Okay, now when we get here, velocity is, do it, downward. Do your right hand rule again, thumb down, fingers in, force now to the right, and we get maybe some motion like this. You keep this pattern going. Now it's going this way, force inward. You notice that this thing always moves in a direction perpendicular to the force exerted on it. All right, or always has a force that points perpendicular to the direction of motion, and that's the very definition of circular motion, right? So if the field extends far enough into space and is uniform, which are assumptions that we can make, we get perfect circular motion. All right, very different. Even though this is a uniform field, it's not the same thing at all as an object, a projectile, right, in a uniform gravitational field. That'll undergo parabolic motion, right? Another good physics word. But this is definitely circular motion as the direction of the force changes. If we have a mass that moves through a gravitational field or a charge that moves through an electric field, the direction of the force on those things will not change. All right? In this case, the direction of the force does change because it depends on the direction of the velocity. All right, so we can apply, yeah, sure, circle. We can apply some circular motion theory here and say that, well, that net Fc is MAC, or really that the magnetic force is mv squared over r, or that QVB is mv squared over r. Yeah, good. And of course, you know, we can get rid of a v there and do a little algebra. All right, so that's a very common connection to have to make between two topics with some darn good physics. All right, circular motion and here magnetic forces. All right, so we need to know what speed a proton would need to circle Earth. Did we do this one? Well, if we didn't, yeah, we did actually in one of the previous sheets, but not the worst thing to go back over it. So I'm going to go right from here and say that, well, QB is mv over r, and we want to know the speed. So here, speed is QB r over m. Right, and we know everything because it's a proton. We know the field strength. We know the radius. Now, this part here just means we have to add that 1,000 kilometers to the Earth's radius. So there's our total orbital radius. And mass of a proton, 1.67 times 10 to the negative 27 kilograms. Yeah, and we get, let's see, V is 2.8 times 10 to the 7th. Okay, fair enough. Yeah, so, you know, what does this look like? Viewed from Polaris, the North Star, right? The North Star Well, let's see. That means this is our geographic North Pole, which is really a magnetic south. Forget about that. That means that the field, um, let's see, fields go from north to south, right? From magnetic north to south. So that means the field comes, you can't see it because it's on the other, behind the screen, there's our magnetic north. The field comes up and out of the page everywhere around here. All right, and then wraps back into that geographic South Pole at our magnetic North Pole. And let's see, so in order for this thing to move in a circle, fingers out, that puts palm in when the object is moving in this direction. Well, let's see, yeah, if it's a proton, right? This is a proton, so that means if it's doing this, that's going to be velocity down, fingers out of the page for the field, and force inward. So that means that the circular orbit would have to be in that clockwise direction. Okay? Okay. Yeah, now we talked about this in fourth block today for sure. What about gravitational force? Is that gonna mix things up? Well, if you go back to that same worksheet on QVB, we asked in the first question, what's the gravitational force acting on a proton or something like that? And then we compared that to electrostatic forces and to magnetic forces. And the magnetic force in that problem, FB, was on the order of 10 to the, I want to say, negative 17th. And the gravitational force was on the order of 10 to the negative 30th. Well, that was for an electron, I guess. So let me change these to, this would be for a proton 26th. I'm just doing m times g, 10 times the mass of a proton. Mass of a proton is about 10 to the negative 27th, right? There's that. So, and then this magnetic force would be somewhere in there, I think. All right, and so the deal is, the answer to this is no, because FB is about 10 to the 13th times bigger. At least moving at some speeds. Now the speed plays a big factor in this, but in general, what seems strange is gravitational forces are kind of the weakest forces around. Right? They dominate our lives and they seem like they're strong, but kind of, I hate to say pound for pound, but unit for unit, I'll say magnetic forces and electrostatic forces are way, way, way stronger than gravitational forces. Okay, so we can forget about that. They would change our answer here by a factor of a 100 millionth of a percent or something like that. Okay? Okay. Now, another good application of this connection between circular motion stuff and magnetic force stuff. And this device, this is a real device, or at least this is the innards of it, the functional part of it. It's called a mass spectrometer. All right, and its job we talk about in the end. So maybe I'll wait on that. Yeah, I think I will wait on that. But here's one big part of the mass spectrometer. First, what you have is two oppositely oriented magnets where their poles are, in this case, like you see. And then those positive and negative plates are literally metal plates, charged plates that are oriented as you see there. And so what that gives us is, I'm not going to draw it because it would get to be kind of a mess. We get a magnetic field in this case that is oriented into the page from north to south, and we get an electric field that's oriented downward from positive to negative. Okay. Now what we do is this part of it. Well, first of all, we can shoot. Let's say we shoot positive particles, nuclei. Let's fire them through this thing that we call, or that I call, the velocity selector. All right. This part of the mass spectrometer I call the velocity selector. It's not the technical name for it, but here's why I call it that. All right. If we look at a particle in that part of the apparatus? Well, there are two forces, and again, let's forget about gravitational forces. They are a million times weaker or so than magnetic and electrostatic forces. So here's the deal. This positive charge that goes through there, well, the electric field created by those charged plates points downward. This is a positive particle. Therefore, it feels an electrostatic force that looks like that. Now, there's a field into the page. Sorry, again, there's a magnetic field into the page. Okay, we have a velocity. And again, important, this blue velocity vector is not a force. Okay, it just represents the object's velocity. So velocity to the right with our right thumb. The field points into the page, right finger's into the page, and therefore the magnetic force exerted on this thing, FB, pushes up. Okay? All right. Now, the reason we call it a velocity selector, hang on, wait for it, is that different things happen if particles go quote-unquote too fast or quote-unquote too slow. Because one of these forces depends on how fast the object moves. And what we can do is write or quantify, or at least give an expression for how strong each one of these forces is. Well, this one goes as QVB. All right? Electrostatic force goes as QE. So notice, if particles are going, say, quote-unquote, fast, well, that means that QVB gets big, all right, or bigger. And what we can say is particles that are too fast accelerate upward. Particles that are too slow, like even a stationary particle, will be affected by this electrostatic force. It'll be pushed straight downward if it's not moving at all. Okay, so particles that are too slow, I mean, even if it's moving but say quote-unquote slow, QVB could be smaller than QE, and these particles will accelerate downward. What I should do is make a little note that what we're saying here, the reason this is because FB will be greater than FE. This is because FB will be less than FE. So you guessed it, there's some perfect, just the right speed where we can get FB equals FE. And what happens there? Well, this particle is what we call undeflected, right? It goes straight on through there. All right, its path is a straight line path. So that's why I call this thing the velocity selector, because we can choose well, speeds that we know. All right, and the speed is going to be, well, just like it was, but well, sorry, not like just like it was before, but we can say, and does that happen over here? Sorry, just give me a second. Nope. So what happens is this means that QVB equals QE. And therefore, assuming that we control the strength of the electric field by controlling the voltage applied across those plates, and that we control the strength of the magnetic field by, I don't know, knowing what kind of magnets they are, or I don't know. Assuming we know those two things, we can actually say, all right, I know what the speed of those particles that are coming out are. All right, it has to be that speed. That's a pretty darn popular question to talk about, all right, on AP exams. So yeah, that's one you want to definitely have in your bag of tricks. Okay, so the nice thing about this again is that when particles come out of this what I call velocity selector, we know exactly how fast they're going. All right, now the second part of this thing is once these particles come out of the velocity selector, they enter into this place where, in the way I set it up, we have a magnetic field that points out everywhere. right? And then we also put in this thing that I'll call a detector plate. All right, and what happens here? Well, we can use some right-hand rule to say that, well, velocity of this thing is to the right. Uh-oh. Oh, yeah, no, we're good. Yeah, we're good. So velocity of this thing is to the right. My thumb's to the right. Magnetic field's out. My fingers are pointing at me. That means in the beginning, this thing is pushed downward, and then it, well, what we said before, it ends up following this circular path until whammo, it collides or smashes into this detector plate, right? And the plate you treat with something, you know, like old TV screens. The inside of them were treated with something that lights up when electrons hit them. Well, this, you know, this stuff, let's say, is some sort of phosphor, and when charges hit it, it releases light. Okay, and so what we can do is, based on where this thing hits, we can end up doing something like this and say, all right, well, this thing had a path with a certain radius r. All right, now something else might have a different path with a different radius. Wait for it, come back. Yeah. So we might have something like this that had a radius, and the fact that it's twice as big is just a coincidence. I'll call this R1 and R2. So different particles that come out of there at the same speed, might end up hitting in different places. All right, and we'll talk about why that would happen. So now, in the spectrometer, in this part, you know, this is really what I call the spectrometer, right? We have the velocity selector in the beginning. This part where the magnetic field is in the detector plate, that's the spectrometer. So what happens out there? Well, that's where we go back to our circular motion part, right? We have an object that, let's say when it's right here, our positive particle, it's moving with a velocity that way. The force exerted on it is this way. There's our FB, what a mess this diagram is. So what we have is a thing where we can say the net centripetal force is MAC. Well, that's really a magnetic force, is MV squared over R, and this is QVB is MV squared over R. We can get rid of one of those V's, and we can say that, well, let's see, that, well, you know, I guess it sort of depends on what we want to do here, but we could find, well, any of these things, I guess. We already said we know what B is, because we'll control it. We know what V is, right? We have this now. QB is MV over R. We know what V is because of the velocity selector. We know what R is because we can measure it. So what we can get down to is, you know, what do we want to find? We could really find either the charge of the thing or the mass of the thing. All right, and here's where the whole point of this mass spectrometer comes into play. What the heck are they for? Well, here's what they're for. All right, you fire a bunch of stuff through there that are nuclei of the same element. Well, same element means we know the atomic number, and that means we know the charge because we know how many protons there are in the nucleus. All right, so if these are all things, all particles of the same element, that means we know Q, and that means that based on where these objects hit the detector plate, based on the radius of their circular path, we can find their mass. All right, and this is what the reason we use this thing is to find different isotopes of the same element. All right, so I'm gonna say that at the very bottom. Different isotopes. Right, and an isotope, hopefully we remember, are well, they're the same element. The only difference is there are a different number of neutrons in the nucleus. All right, same number of protons, of course, that's what makes them the same element. But if there are a different number of neutrons, we get a different nuclear mass, right? And therefore, that changes, right? And if M gets bigger, well, so does R. So different isotopes will, I'll say, travel paths with different radius. All right, so we can use this thing to figure out literally, I mean, how many neutrons are in different different isotopes of an element. Okay, based on how far down on this detector plate they hit. Okay, so this is a doozy of a slide, but the big parts, you know, are here, right? Talking about what the velocity selector allows us to do, and you know what it allows us to control for, and how we can calculate how fast things are going, and then again being able to connect circular motion stuff with our new magnetic force stuff. Okay, so there are some questions that well, that relate to the stuff that I'll give you when I see you next. I gotta be honest with you, I'm not feeling too confident about there being a snow day on Thursday, but I hope I'm wrong. All right, folks, and I know there was a slide right before these, probably in your notes, but I yanked it out of there, so don't worry about that. Okay, okay, see you soon.